All right. So things I need to go here. So we did finish Wednesday's lecture, right? I was not behind that one. So the beginning, it takes a little bit for me to adjust my speed with the class. So I asked if you needed more practice for transfer for the block diagram reduction. So what I did is our class participation actually was due during the class, but I changed it and made it due Monday, beginning of the class. And I gave you a question that you actually need to think a little bit. So I thought it would be stressful during the class time. And then I didn't want to just work on the weekend. So if you wanted to do before class on Monday, you can. You would need more than 10 minutes for that. So don't leave it for the last minute. Even if you're good in block reduction, the question you actually have to draw the block diagram, then do block reduction. All right. So you'll check that and you'll see there's no password requirement. We can do that after class. But another question that you can come across and see about block diagram, at least concerning to our class, would be something like this. So I chose this from your textbook. So this figure demonstrates the block diagram of a brake model system. So there are two brakes, two wheels, right? So, or two system, front wheel system and rear wheel system. And you see that the block diagram, the actual car is simple, something that you might have seen. So later on, we can fill into these boxes what each transfer function is, but from the system engineering, the bigger picture, you see that they're not very complicated. So it's a control system, brake control system. Now, we want to know what is the transfer function of the system for the front wheel brake system to the input, to the reference input. So I'm asking, what is the transfer function of this output respect to this input? Because there's another option, could be the rear system, right? So we could have, I could ask for different output. Now you might say, oh, this is two output. It's actually not. It's one output to the braking system. We divide it in two. So this is a still CISO system, single input, single output. The output is controlling the brake system. We just divided the brake to rear and front. Now, if we want to solve this, what do you think we should do? So this is your reference input. You have a bunch of blocks, and then you have two outputs. You haven't seen this, at least in this example itself. What would be your approach? Yes. So you want to divide it from here? So how do you solve that? That's what you mean. You mean like to go this way and then go the other way. All right. Any other suggestion?
Would you make them one and then once you're done, you again?
If you do that, you need to know the relationship between the two, right? The two outputs. So actually your suggestion was not a bad idea. Let's go that way, and we kind of come across what you said. We want to write one based on the other, and then once we have the relationship, we can just solve it, right? So if I go and try to divide it into basically what I'm doing, I'm going to say that, okay, let's look at the loop on the top, right? So I know this is R H of S, but if I like kind of divide it from here, I'm not going to actually divide, but I'm just saying that if I go through this loop, what's going to happen? So I'm going to need to know what's the signal over here, right? What is this signal? Because then I'm dividing, and my division happens here, right? So I don't know what this signal is, but I'm just going to say, how about this was U of S? I don't know. Give it any name you want, right? And this is something we're assuming, and it, as you guess, is going to disappear. For now, we're going to use it as a placeholder. So if we do that now, if we follow what you said, let's write these two output from here and try to bring U into the equation. So I can write f of f. I'm going to drop all the s's. So f of f, this output up here is G2U, right? So this is U of S, G2 becomes this signal, G2U, which is basically my f of U, right? And this does not impact because that is just a takeoff point, so it's the same signal. So I can write f of f is g to u, and also I can write f of r is g through u, right? I can write that. Now, we can write u based on one of these output, right? And then we can place it in the other one. That's how we're relating the two output together. So since I'm looking for f of f over r, I'm going to make sure everything is based on f of f, right? So I'm going to write my f of r based on my f of f. So I'm going to say u from this equation is going to be 1 over g2 f of f. Then from here, I can say if I had f of r anywhere happen, is going to be g3 u, which is 1 over g2 f of f, right? So I found the relationship between these two input. Now, output, sorry, I connected them. Now I can go about and solve the upper loop. So from the block diagram, we can write the equation for f of f for the top loop. So from the block diagram, I can say f of f is, so how does this get created? R goes in here positive, this part goes here negative. I also have a signal coming from here, negative sign. So I'm going to create all three of those. So R minus, from here I have H2 multiplied by f of r, because that's basically takeoff point, right? This value of this signal is f of r. So H2FR goes here negative sign. Also from here, this is f of f, H2, right? So this goes here, becomes, so far, this is this signal. Now I'm multiplying at G1, and I'm going to G2 to go to f of f, right? So multiply with G1, G2. So if I call this, I'm just going to call this a star. So I'm going to put a star here so you know what this is. So this is star is that signal and goes through G1 block and then goes up here, G2 block. So I solved the upper loop. Now, what can I do here? So again, let's look at what we were asked to do. We were asked to find f of f based on r. So if you look at here, down here, f of f, or the only odd part is f of r, but I already have the equation based on f of f. Replace, and then just organize and find the solution, right? So that's what I'm going to do. So I'm going to sub for fr, going to be of f r minus h2 g3 g2 f of f negative, then you have h2 ff times g1 g2. Now I can just write this down. Everything is based on what I want. G1 g2 r negative h2 g1 g3. G2 cancels out here. Negative h2 g1 g2 f of f. So now to write the transfer function, I have to create this relationship. So output over input. So here, I'm going to bring all of them to the other side, and r is in one side. So if you do that, you will get f of f over r. So you see the the coefficient of r is g1, g2. So if you know how I got that, and then will be 1 plus h2 g1, g3 plus h2 g1, g2. Now this is the transfer function. Yeah. For that. So that's another example that you might come across, right? Your homework is also an example that you will solve, and then if there's a question you have to think about, what does that mean? And then you have to give me your analysis and your answer. All right. So I want you to always, when you're solving something, whatever is on the paper, I want you to look at it and analyze. Does this make sense? Does the thing that I have? All right. Don't just write things on the paper. I have an equation, it should fit. Things should make sense. If they didn't make sense, then you need to either do it again or come talk to me. So does this process make sense? Right? So kind of question you might get, or I want you to think about when you see block diagram, can you reduce them using block diagram method? If I ask you for specific output to input, can you find the signal inside your block and then kind of divide them into sections or however section needed? And can you write a transfer function from an actual system? So I have actual system, like your class participation, draw block diagram, do the reduction, find the transfer function. If you can do all of this, you're good, at least in terms of block diagram. So we have two different kind of reduction system. One, we will reduce a system using block diagram, which is this. Then next week, we are using Mason's law. How many of you used Mason's law before? Maybe one or two, maybe they taught you in system, I don't know. So we kind of, it's a kind of different approach, but will result in the same thing. But that you're using networking and graph analysis also. So it's kind of a broader overview. That's why I started with this. Hopefully most of you are familiar with this method. All right. So class participation, no need to for any passcode. Now for today, before we dive into transfer functions, poles, zeros, stability, and blah, 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 all of that, I'm going to talk about time domain, frequency domain, and S domain, and how they are related. I want you to understand what each of these are before we jump into transfer functions and like try to find pole zeros. I want you to understand what a pole zero is, how would it affect your system. In order to do that, you need to understand the domains first, all right? So all of us are living in time domain. So at least one of the dimensions we live in is time domain, okay? We feel time, right? So think about you're going to your friend's house, you start from, so you get to the beginning of the street, 10 meters, you keep going, the distance is decreasing, right? And you're getting closer, and then finally you arrive. So how long it took? You say that, okay, how much is the distance? What was my speed? I have the equation to find the time, right? Even before you go, you can calculate. Oh, it's 1 mile. Going like by walk is gonna take me this much, or that's my speed, and then you can calculate time. So it's easy to understand things in time domain. That's what I mean, all right? So if we have problems that are in time domain, we can easily solve them. We can say like, hey, distance for that example is going to be speed times time. So this would be a function of velocity and time. When it's function of time, we are in time domain. So all of our solution will be in time domain as well, all right? But now let's imagine, have you seen Jack in the Box? We all have seen, right? Just hit on the head. Let's say there is no friction, and it's gonna go forever up and down, right? Dun, 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 dun. How do we show this in time domain forever? If you want to plot it. You need a lot of paper, right? If you wanted to draw, let's say this is the hammer, that's Jack in the Box. If I hit on top and there's no friction, it has to go forever, and that's how I will show, right? Sometimes this is very inconvenient way of representation. So we might need something else. Now, think of that as, okay, let's say if I hit with a specific force, this is going to be my trajectory, right? And then I can also hit it with a higher force and it go faster, right? So you hit it once, it's going, and then you hit it again, but like with higher force, it starts going fast, and you want to show how these two, like what is the final position tracking of this object. You say that, okay, this plus this is going to be something like, right? Two signals. Now, what you did here is said that basically this is, we have time, time domain. You know where I'm going from, right? So if this is your amplitude, A1 and A2, you can mention this and represent this in frequency domain, right? How do we do that? So we find the 21 and we find A1, and that will be the specification of sine or cosine wave, right? And then we can calculate the frequency related to this, and we can show, hey, this is moving with this frequency. I don't need to say anything about time. You don't need to know anything about time. You just need to know the frequency of this, right? So I easily could represent this problem from time domain to another domain, and it doesn't have to, you don't have to be concerned like, oh, I need a lot of paper to show like the position of this object. You don't need to. You mentioned it in frequency, and I understand that. I don't need time. So basically what happened here is, instead of saying, hey, this is the Jack in the Box tracking after hitting it 2 times, you can say, you know, if this was amplitude, and then I was ampli, and if this was frequency, then for 1 over T1, right? Here you had A1. That's the frequency for 1 over T2. That's A2. Here's our frequency. So you could show different signal with different frequencies were applied to this object. Very simple. And you and your audience will understand. Now, the beauty is that these two are equal, right? Are they? Are they equal? Are they representing the same motion? Yes, they are. One is in time domain, one is in frequency domain. You can convert them. You can convert from time domain to frequency domain if you have the information from both sides. Now, how do we convert from one to the other domain? How do we go from time domain to frequency domain? Huh? No. Fourier transfer. Things, not Laplace, no. Fourier. So if you had signal and system, that's probably all you did, right? Going from time to frequency or using Fourier transform a lot. So Fourier will take you from time to frequency. How do we go from frequency to time? The inverse of Fourier transform, right? You can go from frequency to time. So with that, so transformation is basically the mapping to go from one domain to another, right? So every time you hear transformation, you are mapping something to something. Now here you're going between time domain and frequency domain. So most of you are familiar with these two integral. I'm not going to actually go inside this integral. I'm going to explain what these are, and then how do we connect Laplace to this. So we will go to Laplace after this. Now, so if you are in time domain, you have a continuous signal. Let's say we are in time domain, that's how our signal looks like. It's 0 for some time, and it gets another value for the rest of the time, like a step function, a very simple function, right? Now, when you go to the frequency domain, you will have to show it with 2 different graphs, right? Do you remember what those graphs were in frequency domain, David?
The magnitude phase.
Yes, the magnitude and phase. Both of them are in frequency. So the horizontal axis is frequency. For the magnitude, the magnitude could be in dB or could be volt per volt, or the magnitude, which is unit of 1, no unit. And then the other one is the phasor, the angle between the signals, right? So now we go from one graph to 2 graphs when we change from one domain to the other domain. Right, these were the specification of this transformation. Agreed, everybody? Right? So if you haven't had signal system, if you don't know what Fourier transforms are, don't worry, because we're not going to actually use them. We're just basically using a definition. So think about, I'm trying to think of transformation in a sense of something that we use every day. Let's say you have a Word file. You use a program to convert it to PDF, right? That program is Fourier transfer. It's converting your Word file to PDF, and you can also extract PDF to Word if it's not all locked up, right? So this is a transformation. So think of it. If you don't know what Fourier transform is, just think of it as this, this mapping. Now, excuse me. Now for this, I'm gonna solve an example so you can see what happens. So let's say that we have a decay, exponentially decaying signal or function. So what is the equation for this? Do you remember? Can anybody remember? This is time. What would give you this purple graph? Huh? Yes. So e to the negative at, right? I'm just going to say negative t. So a is 1 here, right? And let's say that, okay, this was our function. Now, if I wanted to have a signal that only is decaying for time greater than 0, for time less than 0, I wanted this function to be 0. But right now it's not, right? What can I do to do that? So close. Impulse, but after 0, impulse, right? Make sure that it's just constantly 1, 1, 1. So when is that impulse with the same value? What is it called? Step. So step comes from impulse, right? I know you meant that, but so if you add this to it, I'm gonna do green, 0 for all time, and let's say 1 for the rest of the time, right? And this is a step function. Basically, we're going to show it with u of t because I just said, well, I'm going to delete 1 so it wouldn't be confusing. So u of t, a step function, is just says that 0 for time less than 0 and a fixed value for after time starts. Could be 1, 2, 10, whatever number, right? So when these two are mixed, convoluted, right? If you have two boxes, two blocks, they will be multiplied, basically convoluted. And then the solution would look like this. So this is e negative t u of t. Well, I can show the other way around, but it doesn't matter. Because if it was, so if it is transfer functions, well, if these two are functions, they will get multiplied, convoluted, and give us the final result. So now this is how it looks like in time domain, right? Let's convert this to frequency domain and see what happens. We just want to know what will happen. First of all, how many graphs would you expect to see when I go from time domain to frequency domain? 2, right? So if you know the answer, please say it so you will participate in the classroom and won't fall asleep. All right. And also, it is a good feedback for me to know how much everybody understands from where I'm explaining. All right. So I would expect to get 2 graphs from this. Now, how do I do that? How do I go from time domain to frequency domain? Okay, so let's say Fourier transform, right? I have to transfer. So do I write that integral? No. What do I do? You look at the lookup table and the chart and find out what is each of them, because you can multiply them, right? That's the beauty of the integral. So we're going to do that. So from the lookup table, oh, my handwriting when I write fast is really bad. So ut times e to the power of negative at is going to be 1 over a plus j omega. How do you know, Dr. Z? I forgot the lookup table. It's okay. It's here. You can use it. It's also in your book, but I thought it would be nice to have it here. Now, what is A is 1. So actually have the Fourier transfer of my function in time domain, right? So I know that f of ft for Fourier transfer of this negative t is going to be 1 over 1 plus j omega. Great. I have the transformation, right? So I want to represent it. When I represent in time, I had one graph that was 0 plus the decaying value. How do I get the graph for my frequency domain? From this information. So you have the function. Now, how do we show the two graphs? How do we show magnitude and phase from this? You remember? So these are the things that I want you to know, remember, and if you don't, this is where you want to learn them, because we will do this. Right? We will use it. We will use finding magnitude and phase of a function, because this is going to be your transfer function soon. And you want to know how to plot it. Because for us, it's a lot easier to analyze our system by looking at the response. So plotting it is response of the system, right? So you should be able to go easily from transfer function or from a function to how do I plot it. Time domain is very easy, right? You probably remember. When I say sine, you do this. Or is it e to the power of negative something, you know how it is. But if I give you this that has omega in it, you actually have to do that part. All right. So for, if you remember, if not, you're going to do that. For phase, we needed to write A10 of the imaginary part over the real part. Like some of you are like, I remember now. And then for the magnitude, you would write real square root of real to q squared, imaginary squared, right? Why do I care about magnitude and phase? Because that's the two parts that I try to represent my function. Now, 1 over 1 plus j omega, which part is my imaginary, which part is my real? It's kind of mixed up, right? You need to simplify this. Do you remember how to do that? Yeah. So multiply, is that what you mean? Yeah. Yeah. Why do we do that? So we see that our j appeared in the denominator, right? If it was in time, it was 1 plus j omega, super easy, right? It's not, it's in the denominator. So if that's the case, you grab the denominator and then, so this is equal to 1, right? That's why I can multiply it. But doing that, it helps me to simplify this function. And then the imaginary part will appear on the numerator. That's the whole goal. All right. If you already knew this, this is a review. If you didn't, that's the process. You should be able to do this. All right. And you shouldn't be spending too much time doing that. So this will give me 1 over j omega, then 1 minus or plus omega squared, because this gets j to the power of 2 is negative 1. Now, can we convert that? Now, can we have a real and imaginary part from this? Yes. So it's going to be 1 plus omega squared. That's a real number, right? Minus j omega over 1 plus omega squared. That's the imaginary part of it. Now, question, what are omegas? What is our omega? Frequency, we are in frequency domain, right? So when you want to plot, so do you remember impulse function? And we said that for LTI system, we are looking at all the frequencies at all time. So this frequency is all the frequencies. That's why we can plot it, because we can say from 0 to whatever frequency. Let's find the response and then just connect them together. So this omega is not one number, it's a range of frequencies, all the frequencies. That's why we can plot. So now this becomes our real part. This becomes our imaginary part. And don't forget this negative sign is part of that, right? So negative omega over 1 plus omega 2. So from these two, I can create phase and magnitude equations, right? I'm almost done. Once I have that, I'll just plot it. So imaginary part, negative omega over 1 plus omega squared, real 1 over omega squared. So this is going to be A10 of negative omega, right? Yes. And then for this one, so real to the power, so I'm going to write it very quickly here. 1 time squared plus negative omega 1 plus omega squared. All right, so if you do this, you will get to 1 plus omega squared over 1 plus omega squared, which is 1 over 1 plus omega squared. Right, so this is basically 1 plus omega squared, 1/2. Either way you can write it as acceptable. So I found 2 functions, one for phase, one for magnitude. Now, if I give my omega from 0 to infinity, right, then I can plot these 2 magnitude and phase plots. So if you plot them, here is the plot. So this is our magnitude. This is our phase. So this is the phase equation, this is the magnitude. Going from time domain, this equation and this plot, we transferred to equation that, a function that is function of frequency and gave us 2 plots. So we have more information about our system. Now, every omega, every frequency on the frequency line, we can use it and see what's the magnitude and phase of our system there. So this is all good. We all agree how time works and how frequency domain works, right? So now we're gonna, yes.
What does it mean to have negative frequency?
Have negative frequency.
On the graph, kind of like the omega. Is there like negative omega?
So I said if we had negative omega, it would continue like that.
Okay.
We don't have, but if you had negative numbers, it would go that way. So we're gonna use this, like you see this, that's why I put it here. There's kind of a mirror of the positive side, and you're gonna see that appearing in a few slides. So your omegas just go very, very, very small to 0. They won't go negative. But if you had, you'll see that again soon. Now, 2 of our domains solved. We have 1 more domain, S domain, right? So you remember that transfer function are in Laplace domain, S domain is Laplace domain. We all agree, right? You all remember that. Now, what is this S domain is made of? S domain is combination of 2 things. It's combination of an exponential term and a frequency term. Now, do you remember our example in time that was exponential? And do you remember our example that when we convert to frequency, it becomes a frequency? So we are basically saying that this S domain going to represent both of them. All right, so it's a 3rd dimension, if you want to think about it. We define a symbol S, arbitrary S domain, Laplace. I don't know why is S is not L domain, but let's say S, there was a reason. This is sigma, which is the representation of our exponential effect. I want you to remember it as an exponential effect because we'll see why, plus an imaginary part that shows the frequency term or frequency effect of our system. All right, now, just a reminder, if you have e to the power of j omega t, you can go and write this in sine and cosine function, right? So you can write cosine of omega t plus j sine of omega t. Just a quick reminder of that. So these are exponential function if they had imaginary part. Now, if your exponential, so if you have exponential function that has imaginary part, it can be decomposed to a sine and cosine way, right? Now, if you have exponential function that has a real part, like at, negative at, that just acts as as decaying or growth, right? So e to the power of s, which is a sigma, a real number, plus j times some number that is representing frequency, will represent exponential plus sine cosine, which is a frequency, right? Now, for exponential to the power of real numbers, we are going to have something like this. So if 0 was e to the power of 0t is 1, right? You're right at here. If you have positive numbers, you're exponentially growing. If you have negative number, is decay, correct? Yes? Now, these are important because once you know this, by looking at your at that S, that polar 0, you can understand the response of your system if you understand which of these two parts are doing. So the first part, sigma, is the exponential part. If it is positive, it's growth. If it's negative, it's decaying. Then the imaginary part is sine cosine, right? It's about j omega t. Now, if we separate these, think of it. So if we have S, 1 plus 2j, right? So 1 is your sigma, 2 is your omega, right? Now we can say that this looks like e to the power of 1t convolution, right? Times that sine cosine, because e to the power of 1 plus 2t is equal to et times e to the power of, this was 2j, sorry, 2j. Is equal to this first function times the other one. So the response, so the behavior of the system is either going to be this or this, nothing else. So by knowing that, you already know how the solution would look like. That's why it's so important for you to know. So this will give you intuition. When you're designing, you're saying that, oh, I want my controller to do this. Then you remember, what do you want your response to look like? And you kind of reverse engineering this thing and go back. You practice this a lot, don't worry. But I want you to remember that this is the fundamental, the basic. You need to know these things. Now, if we have a negative response, so if this was a negative sign, we have a decay, look what happens. We are gonna have something like that, which is probably favorable when we design a controller, right? Why? So you are kind of converging to something, right? Look at here. You're converging. Here is going haywire, right? So that's something to avoid. This is something that's favorable. So I'm showing you the behavior of your system, and when you design, you basically design where my S is going to be. What's the value of my S? That's called pole placement, right? Why are we using pole placement in designing controller? Because we know which behavior we would like to see and which one we'd like to avoid. And that's where it comes from. So that's why for me, definition and fundamental are really important. Once you understand this concept, the rest of this will be really easy for you. Sorry. So the S-plane basically is the combination of that frequency and that exponential together, right? Now, the cool thing is that, well, let me remind you Laplace, and then I'll show you the cool things. So you remember Laplace transform. You've heard it. There is a transform in there, right? You remember that software that converts Word to PDF? So this Laplace transform does something, transforms something to something. It transforms frequency to time. Sorry, time to S domain. So your Laplace transform transforms time to S. Your Fourier transform time to frequency, right? Can we find a relationship between them? Because there should be a way, right? Because I'm going from here to here, I'm going from here to here, that's transformation, right? Mapping. There must be a way that connects these two as well. It's just logical that way. And the good news is there is a connection between them. So I think once you see that connection, this whole Laplace transform will become a lot easier for you. You can use the lookup table and everything, but really like this is the base of what you should understand. Let's use our example here. Let's say S is sigma plus j omega. I'm using my Laplace transform, right? I'm using the integral. So I can write negative infinity to infinity f of t e to the power of negative sigma plus j omega t dt. Now I can say so depending on your sigma, this e to the power negative sigma could be representing a growth, right, or decay. All it's doing is making this function f of t to be growing or decay. But look what happens after. Does this sound familiar to you? Now is Fourier transforming that function. So Fourier transform exists inside your Laplace. Now, how can I make this exactly to look like my Fourier transform? What can I do for this integral to look like that integral? But it still is not look like. I want them both to be exactly the same. Someone said what? Sigma to 0. So if sigma, so let's say at sigma equals 0, then fs is, so e to the power of 0 t is 1, e negative j omega t dt. So what does it tell you? Fourier transfer is the Laplace transform as sigma equal to 0. So we only have frequency. Now, if we have other sigmas, 1, 2, 3, negative 2, 3, negative 4, we just have more of the same thing, like in parallel. So one of these is only called Fourier transform. So if you think of, so if this is sigma equal to 0 line, I'm going to do this. So this is sigma 1, sigma 2, sigma 3, like negative 1, negative 2, negative 3. So these are slices of these 3 dimensions. One slice is your frequency domain. But once you do the other one, now you see exponential decay and exponential growth. Now you have S domain, the Laplace domain. It might not make sense. It's very counterintuitive, but I want you to think about it. All right, so this is something that I want you to look at it for 5 minutes, and then maybe at the end say, okay, I can understand this at some point. All right, but you're well familiar with that sigma equal to 0 slice. You have seen it. That's your frequency, just the frequency domain. So that's why we showed the negative part, just to get it, because it's the other line. Now, once we define our transfer functions in our S domain, that's the S domain, we will say, if you have a root at this plane, what does it mean? Oh, our system is unstable, right? So that's just a use of this new domain and new plane. You only can use all the equation in estimate only for estimate. So your transfer function is estimate. You cannot use any of the equation in time domain for this or frequency domain for this. You can convert, but you can't just randomly use time domain equation for estimate. Any question on this transformation from one to other and how they are related? So really, that's the end of today's lecture. So all I brought was to show you the three mapping, and I want you to understand their relationship. So if I ask you about frequency domain and how it's related to S domain, I want you to talk to me about this. You don't even have to do the integral, but I want you to talk to me about this and understand what happened here. All right. On Monday, we will actually work with transfer function, pole zeros, and how they affect the stability. And then, does everybody have, most of you have access to computer that can bring or iPad? So we're gonna probably use MATLAB to do a lot of this in MATLAB and C, because plotting is a lot easier in MATLAB. All right, so bring your iPads if you have.